Hello everyone! In this lecture we will study the content security policy and the attack techniques it can mitigate. The topic of this lecture is motivated by the understanding that no matter how hard we try, it is very hard to avoid all and every code injection or XSS vector in a website. This is especially true for legacy projects with complex code that are constantly being developed and updated. Therefore, we would like to apply some measures that would make the exploitation of an XSS vulnerability much harder. And this is where the Content Security Policy, or CSP, can help us. A web application can enable a content security policy by returning an HTTP response header as shown here. There are many options that can be configured, but let's focus on this specific policy that is defined by this header. As you see, it specifies only script source self. What it does is that it forbids execution of all inline and foreign external scripts. So none of these four methods of executing JavaScript code will work if this content security policy is enabled. Neither code between script tags, nor external scripts hosted on another website, nor code inside an event handler, nor JavaScript and data URLs will execute. So essentially there is no way for an attacker to execute JavaScript in our web page using XSS. The attacker will still be able to inject HTML, but if the attacker is unable to execute JavaScript, the impact of XSS is severely limited. But here you may ask, if an attacker is unable to execute JavaScript, how can then the code of the legitimate website execute JavaScript? The answer is that this policy provides an exception. It allows execution of external scripts, but only loaded from the same origin. So JavaScript loaded from a file that is hosted on the same origin website will be executed. Now, why can't this exception be exploited by an attacker? Well, because an attacker using an XSS attack vector cannot upload malicious script files to the server or modify existing files. Therefore, the attacker cannot abuse this to execute illegitimate JavaScript code. Effectively, what we did here was use a response header to instruct the browser that the only JavaScript code authorized to run is the one contained in JavaScript files. Of course, here we assume that an attacker cannot inject arbitrary headers, as doing so would allow the attacker to disable or rewrite the policy. Alternatively, the CSP policy can be specified inside the HTML using a meta tag, but this can be bypassed if the attacker can inject code into the head tag. And also, not all CSP directives work inside a meta tag. For this reason, the HTTP response header is the preferred approach for specifying the policy. Anyhow, so this is a very nice and strict content security policy, but it requires moving all JavaScript code to files. Now, moving this inline script here to a file would be rather easy. The JavaScript and data URLs should not be used in practice anyway, but a bigger problem would be here with the JavaScript code specified in event handlers in attributes such as onClick, onload, and so on. This requires a heavier rewrite of the code. For example, if we have JavaScript specified here in the onClick attribute, we would need to remove it, assign a unique ID to the element, and instead call add event listener for that element inside the external JavaScript code. As you see, making an existing application compatible with such a policy can be quite development intensive. Therefore, it may be very tempting to relax the policy by specifying unsafe inline here, which would allow the execution of all inline scripts and render the policy pretty useless. Well, actually, we can argue that such a policy is still much better than nothing, as it will block XSS payloads loaded from the attacker's website, and therefore limit the size and flexibility of an XSS payload. Anyhow, when developing new web applications, we should follow the principle of keeping HTML and JavaScript separate, which will allow us to disable unsafe inline and is also considered a best practice in web development. To summarize, the content security policy is a very effective measure in preventing XSS exploitation attacks. So if we can develop or modify our existing application so that it follows the policy defined here, then we have done a pretty good job in preventing XSS exploitation on our website. Note that it is possible to relax the policy by specifying here a list of other trusted origins from which JavaScript code can be loaded. And if our website uses, for example, Google Analytics, we will have to include JavaScripts from Google's origins. So the problem is that in practice, complex real-world applications usually require relaxing this policy by adding additional trusted origins here. And this then can enable an attacker to bypass the policy if the attacker can upload or find a vulnerable JavaScript file on that third-party website. A better CSP configuration option is to use the so-called nonce mechanism. Here's how it looks. Instead of specifying here a list of trusted origins from which scripts may be executed, we specify a random nonce. This allows the execution of any script that contains the same nonce value as in the CSP header. So this will execute inline scripts and external scripts from other websites or our own website. These scripts will be executed because here they contain a nonce attribute that contains the same value as here in the CSP header. The requirement here is that a unique nonce value must be used in every HTTP response. If so, then this blocks the execution of injected scripts because an attacker cannot predict the expected nonce value that should appear in the response. Therefore, the attacker does not know what nonce to specify in the attack payload. Of course, the attacker can try to guess it, but there is no chance of success if the nonce is generated as a cryptographically secure random number. Now, the security benefit of this nonce approach, compared to the one shown on the previous slide, is that it prevents the execution of arbitrary scripts from trusted origins. As in this case, there are no trusted origins. Instead, each script execution is explicitly authorized by specifying the nonce attribute. While in the previous approach, an attacker was not able to execute the attacker's own scripts, the attacker could still manipulate with the web application by executing arbitrary scripts found anywhere on the trusted website. Furthermore, these scripts could be executed in unexpected contexts, in the wrong order, and an unexpected number of times. You can imagine a smart attack where, by reordering the execution of legitimate code residing on the website, an attacker could disrupt the JavaScript execution flow, introducing unexpected behavior that could then be exploited in an attack. So this nonce approach is more secure as it prevents such manipulation attacks. However, there are two security considerations when using this approach. First, the inline scripts must be XSS-proof, meaning that preferably they should be static. If the content of the script here is generated dynamically, including potentially malicious user input, then obviously this will not prevent arbitrary script execution. Another note is that the CSP base URI directive must be set to prevent CSP bypass when loading external scripts using a relative path. Here's an example. So if an attacker can inject such an HTML base tag, the result will be that this script here will be loaded from the attacker.com website, enabling the attacker to execute arbitrary JavaScript. To prevent this, we can specify the base URI directive here, which will instruct the browser to ignore base tags that do not match the origin specified here in the header. Anyhow, to summarize, from a security perspective, this nonce mechanism is the best approach to whitelist the execution of authorized scripts. But again, let's say we completely block the execution of any malicious JavaScript. Are we good now? Well, it turns out that even when JavaScript execution is restricted, there are still some other attack vectors that can be used to exploit a code injection vulnerability. CSS cascading style sheets injection is one such vector. First of all, by injecting an arbitrary CSS syntax, an attacker can gain complete control over the website's look and feel, because CSS enables to change the appearance of any element on a web page. But there is actually more that CSS can do. CSS syntax has quite powerful features that can be abused in a code injection attack, more specifically for exfiltrating data using CSS. So here's an example. Let's say a website contains some element that contains a secret value inside its attribute, ABC123 in this example. By injecting such CSS code, an attacker will learn whether the value inside the attribute starts with the character A. Here, the attacker is abusing the CSS selector feature, specifying that for input elements with name equal secret and the value starting with the character A, this background image should be used. So if such an element exists, the browser will attempt to fetch this image from the attacker server, and the attacker will learn that the element exists on the page. In this example, the value of only one character is tested, but the attack can be extended and repeated to uncover the entire value of the attribute. This method works for exfiltrating HTML element attribute values, and the first target for the attacker usually would be stealing CSRF token values that are placed inside the attribute of the HTML input element. Another method can be used to exfiltrate data that is placed between HTML tags. Here the idea is that we can request to load a custom font for specific characters. So here we define a custom font for the character A61 in hex, and apply this font for the div tag. If such a character is inside the div tag, the browser will try to download the custom font, and the attacker will learn that the character is present. In this example, the attacker does not learn how many duplicates of the A character are present or the order of the characters, but there are other CSS tricks that can be applied to exfiltrate the entire string. This is a very powerful method as it works for any tag whose contents can be displayed. And surprisingly, we can also force the content between the script tags to be displayed, thereby exfiltrating secrets stored inside JavaScript code. So what can we do to prevent such attacks? Well, we need to lock down CSS similarly to how we restricted the script execution. We can do this using the style source content security policy directive. What this particular policy does is it allows external same origin styles only, so it prevents the import of styles from other websites. Then it allows nonce-based inline styles only, so only if the nonce attribute of the style matches the nonce specified in the CSP header. And it blocks inline style attributes on HTML tags, so this will not work, meaning that the HTML has to be rewritten, moving CSS code into CSS style definitions, which is also a best practice in web development. As an extra hardening measure, we can add image source self and font source self. This allows same origin image and font loading only, meaning that even if an attacker were able to inject CSS, these attacks would not have worked as these requests to the attacker's website would be blocked. So let's take a deeper look at how we can use content security policy to harden our website against similar data exfiltration attacks. So by preventing data exfiltration, we can limit the impact of an attack in case an attacker has somehow managed to run arbitrary JavaScript on our website. So let's assume that an attacker has somehow managed to bypass our content security policy restrictions and is able to execute arbitrary JavaScript on our website. First, what data would the attacker want to exfiltrate? The target would likely be authentication cookies, CSRF tokens, the entire DOM that the victim sees, or any data that is accessible to the victim on the website. So these could even be gigabytes of sensitive files that the victim has access to on the website. Now, what methods could the attacker use to exfiltrate data from the website? First, the attacker would probably seek exfiltration using post requests, because with a single post request, we can usually submit megabytes of data. So here the attacker could use the JavaScript's fetch API or WebSockets to transmit the data in the background to a server controlled by the attacker. Here we can use the CSP connect source directive to restrict the origins with which these fetch and WebSockets calls can communicate. For instance, ensuring that fetch can send requests only to our own origin. Of course, this will not help if the attacker can find an endpoint on our website where the attacker can submit data that is later visible to the attacker. For instance, if it is a social networking website, the attacker could simply use the messaging functionality available on the website to send the data to the attacker's own account. Alternatively, the attacker could use HTML form auto-submission to submit a post request to a website controlled by the attacker. This, however, will not be stealthy, as the victim's browser will be navigated to the attacker's website. To avoid the browser being navigated, the form can be placed inside a hidden iframe. The iframe element has this source doc attribute, which can be used to create same origin frames with the content specified here. Using this trick, data exfiltration can be performed in a stealthy manner in the background. Here we can use the form action directive to restrict the origins that can be specified in the form's action attribute. The frame source directive can be used to restrict the origins which can be loaded inside the iframe element. So if we had frame source set to self or none, then the stealthy method would not work because this cross-origin form submission would try to change the origin of this frame and would get blocked, even if the frame action restriction was not applied. Note that even if frame source is set to none, the attacker can still create such same origin inline frames using the source doc attribute. However, the attacker would not be able to load same origin web pages inside the iframe, so this would block same origin communication through iframes. Then there are data exfiltration methods using GET requests. So there are quite a few HTML elements and JavaScript objects that can be used to fetch or embed a resource from other origins. For instance, an attacker can create an image object in the source attribute specifying the URL, which will force the victim's browser to fetch the resource and make the request visible in the attacker's web server logs. So here, the attacker would have to embed data into the request URL either within the subdomain or in the request path. The length of a URL is limited to approximately 2 kilobytes of data. But of course, the attacker can create several such requests to exfiltrate more than 2 kilobytes of data. Here we can use these content security policy directives to restrict the origins to which these objects are allowed to make requests. Note that there is the default source directive, which is used as a fallback for absent source directives. This means that we can use it to specify a common policy for all these source directives, except for the form action directive, which must be defined explicitly. Now, as you see, our content security policy can get quite long and complicated. Therefore, it might be a good idea to pass it through a validator before applying it on our website. The validator should also warn us if our policy has any serious holes in it. Now, the third thing about the data exfiltration is that even when we restrict all these exfiltration methods, exfiltration using top-level navigation is still possible. For instance, the attacker can change the location of the current window to attacker.com plus document.cookie, which will leak cookies to the attacker. This will not be stealthy exfiltration, as the user browser will be navigated to the attacker's website, and the amount of data that can be exfiltrated this way is also quite limited. But the attacker could exfiltrate more data by redirecting the browser back to the vulnerable website and then again to the attacker's website, continuing this ping-pong exfiltration loop until the victim gives up and closes the browser tab. Anyhow, the conclusion here is that in practice, if the attacker can run arbitrary JavaScript on our website, we can only slow down the data exfiltration, making it more noticeable to the victim or website administrator rather than completely preventing it. Well, alright, let's say the attacker is not able to inject either JavaScript or CSS. Is there anything meaningful that an attacker could achieve with pure HTML code injection only? Well, there are a couple of HTML-only attack vectors that an attacker could try to use. The first one is an open redirect to a phishing website. By using the HTML meta tag, an attacker can perform an HTTP-only redirect to the attacker's website after a delay specified here. So we call it an open redirect vulnerability when a website allows an attacker to redirect users to arbitrary websites. The problem is that it may increase the risk of a successful phishing attack, because users are more likely to click on a phishing link if it contains the domain name of a legitimate website. Here, however, not everyone considers an open redirect to be a vulnerability. For example, the google.com website has provided an open redirect for years, meaning that here we can specify an arbitrary website to which Google will perform a server-side redirect once the link is clicked. And this has been abused in phishing attacks. For instance, here is a phishing email allegedly from SEB, and if you look at this link here, we can see that it uses this open redirect here. People have reported this to Google, but Google has responded that in their view, this is not a security issue, but rather an intended feature. Nevertheless, there are security guidelines that do consider this a vulnerability that should be fixed. Anyhow, another HTML-only attack technique is data exfiltration using a dangling markup injection, meaning injection of an HTML markup that is not terminated. So here the attacker could inject an image tag with a source attribute that is not terminated. Any HTML between the opening single quote and the next occurrence of a matching quote will be treated as part of the image URL. The browser will attempt to download the image and leak the code to the attacker. So this can be used to steal secrets located between the injection point and the next quote in the returned HTML code. This technique does not work in Chromium-based browsers as they block URLs that contain angle brackets or new lines inside it. As we discussed on the previous slide, we can prevent such data exfiltration attacks by using the content security policy to block cross-origin embedding on our website. Then the attacker could perform a form parameter injection to modify the existing HTML forms on the website. For instance, if an attacker can inject an HTML form tag before the legitimate form on the website, then when clicked, the form will be submitted to the attacker's website, leaking the filled-in data to the attacker. Similarly, by injecting an input element before the legitimate element with the same name appears on the page, the value of the attacker's element will be taken into account regardless of what the victim entered in the form. So this way, the attacker can override the form values entered by the victim. Of course, as an alternative, the attacker could also add new forms to the web page. Foremost, the goal would be to add an auto-filled username and password stealing form, which when clicked would submit username and password, automatically filled by the browser, to the attacker. Here is an example of such an HTML-only exploit in action. The InfoSec Exchange website had a stored XSS vulnerability, but it was difficult to exploit it as the website had a very strict content security policy that prevented script execution and the loading of arbitrary CSS styles. This here is an invisible HTML password form that gets automatically filled in by the browser, so when a victim clicks on this link, their username and password get submitted to the attacker. Now, the neat thing about this exploit is that the form is decorated invisible by reusing the existing CSS styles available on the website. The exploit requires user interaction, but it is quite powerful when you consider that this is an HTML-only exploit, right? To mitigate this attack, we could use the form action directive of CSP discussed on the previous slide to restrict the origins to which HTML forms are allowed to submit data. Then, DOM clobbering, or interfering with JavaScript execution, is another attack technique you should be aware of. The idea here is that we can influence JavaScript execution by injecting HTML elements into the page. This works because the identifiers attached to HTML tags are registered in the JavaScript namespace of the page. This way, it is possible to create new properties and child properties in the global scope and override existing variables if they have not been initialized, or in certain cases, even if they have been initialized. By using this technique, the execution of the legitimate JavaScript can be influenced, bringing it into an inconsistent or unexpected state, which could provide an advantage to the attacker. For instance, consider disabling some security controls that are implemented by the website's JavaScript. As you can see, exploiting this is far from straightforward and is very application-specific. However, this technique can be quite effective if the conditions are right. To summarize, these are some of the most popular HTML-only attacks, but most of them are far from straightforward and may require social engineering to be effective. The final thing to mention is the permissions policy. It is similar to the content security policy with the difference that it restricts which JavaScript APIs a website can access. For instance, consider an XSS attack payload that requests access to the user's camera and microphone. Since the permission request originates from a trusted website, the user might grant the permission, potentially allowing the attacker to compromise the user's privacy. Using the permissions policy header, a website can restrict access to specific APIs. For instance, this policy blocks camera and microphone access, but allows geolocation access for the website itself and the example.com origin. Origins specified here will apply to any origins the website loads inside iframes, so we can restrict iframed origins as well. There are many APIs that can be blocked, and by default they are all allowed. Therefore, one would need to use a permission policy like this one to block access to all APIs. We will talk more about some of these APIs in upcoming lectures. Note that currently this permissions policy is supported by Chromium-based browsers only, meaning that these restrictions cannot be applied for Firefox and Safari users. Anyhow, with this we end the lecture. Thank you for watching.